Alright, hell yeah. We got material mechanics and we got beam bending. So this is chapter 5 in material mechanics gear. Alright, sweet. So today I spent a pretty good time at the coffee shop, and I'm just going to go over kind of what I usually don't do this format. I think it's better to start from scratch, but you know what I mean. I'll make this video a few times. But anyway, it's just the derivation for bending, and I think it's complex. I don't think I could have done this as an undergraduate. I mean, the whole idea of a derivation is just like, well, someone did something to prove something to get an equation, and that's the equation that we're going to use. Now, yeah, let's walk our way through this, because even as we do, I think one of the things that trips people up or trips me up is, well, material mechanics is like, what's like signs, like what's the sign convention, what's positive, what's negative. So in this problem, like this is going to be like a beam, you know, I mean, let's say it's just like a cantilever beam, and there's going to be some sort of force up on it, load, and we have this upward shape. And so this is kind of the diagram for a curve. Is you know, you zoom in right here, you can take a little slice, and oh yeah. So you are going to have some sort of curve to this shape, and as you zoom in, you should be able to have like a curve of a circle, and that is going to have a radius. Like if you took this little curve and then just kept going all the way around in a circle, you would have a circle and it would have a radius. So for these problems, you use rho as your radius. And when we zoom in, we just take a fraction of an angle. That's what d theta is. If you don't like d theta, use change in theta and just say it's 1,000th of a radian. You know what I mean? That might be small enough to get the job done and big enough to make your mind not melt. You know, the fact that d theta is such a small fraction, it almost isn't even there. Cool. So now we have a wedge of a circle. And I'm even kind of slow on the uptake when it comes to working with radians and circles. But, you know what I mean? Anytime you're working, especially with a little wedge, like, might as well make the whole circle. Like, what do we know about the whole circle? I mean, just because I think that kind of spells it out. If someone was asked, like, well, how do you know this stuff? That was kind of a comment. It's like, well, because I want to know, I want to get to the bottom of something, and I want to get to the top of something. I want to know if, you know what I mean? It'd be like, I don't know, like exploring. Maybe some of those like video games. I remember, like, I can only quote like Riven and stuff. I only played video games, but anyway, where you kind of just explore a room and you want to know everything about it, and you get to a point where you're just like, there's nothing more in this room to explore. And I think with physics and science, that's very important. You know what I mean? Is there anything to explore? So where the hell was I going with that? Yeah. So for a circle, is like, well, you're going to have a full circumference of a circle. And if I have a little slice, well, maybe I know, you know, then I can be like, well, a circle is 360 degrees. If this was a 1 degree slice, I would have 360 of them. Then I would know, like, hey, this slice is 360th of the full circumference. But sometimes I need to do stuff like that just to even wrap my brain around, like, you know, radians and stuff. But all right, so but this arc length is a portion. It's the fraction of that full circle. Cool. What happens when this slice becomes really small, whether it's 1,000th of a radian or a d theta, is that this arc length doesn't really show a curve. It's almost a straight line. And so if we had a xy coordinate system kind of going through this point right here, I mean, yes, it would lift off the page right here, and we would actually get, from here we would get a tangent, and this is also d theta, so that's kind of cool. And I've kind of made videos on that. Like even that is like one of the trickiest things, even from that perspective. If this circle is totally flat, the tangent would be right there. But if we're going and so this would be the radius, you know what I mean? But if this circle has a constant radius and we're taking a point right there, like all you have to do is like say, hey, this is going to be my pivot point. And then let's go up to some other portion of that circle. And you're like, oh, okay, so there is this angle. And so when we swept out, let's say this d theta, we also swept out, I can say like, hey, this angle from here is d theta. So I just think that's kind of a fascinating one to do. That's probably the first thing that got me this hiccup of like, well, if this is d theta, like, cool, I get that's a slice, but how do I know anything about this angle? Well, it's just because what we just showed right there. That doesn't come into play for this problem, but we do want to say, well, I guess the fact that the tangent does sweep up, and so if I have this, this xy coordinate system kind of going through that point, what I'm saying is that this distance dx right here, this flat distance, is the same as that swept up arc. I'm even kind of, and then if we go down here, I'm even kind of taking that coordinate system kind of right in the center, you know what I mean? So if I come right here and then say, hey, we have the center of this is this is the xy coordinate system, sorry, yx coordinate system, because that's what we have. Alright, well actually I might be a little choppy on that, because, okay, so now we're going to look at that little chunk, and so here is that chunk of beam, and it has an arc in it. And, well, I guess one more thing, we're going to, just the way radians work, if you do your angle in radians, like what the hell is a radian? You have a circle, here's the radius. A radian just means if I cut a string that length and then draped it around this circle, I'd get to there, and I'd be able to cut 6.28 chunks of string. That'd be 2 pi, 6.28, 2 pi. And so yeah, so hell yeah. So one radius draped around, that fraction, we're going to call that angle 1 radian. And so if I know my radius, of this circle, I know this distance, this arc length. If someone says, hey, I have 1 radian of a circle, well, visually I can say that's about 60%. But I do know the arc length if I know the radius, because the arc length is equal to the number of radians times the radius. So it's kind of the arc length S is equal to radius times radians. So that's what we have right here. I think this is one of the hardest equations. It doesn't look good. It doesn't make sense. You know what I mean? Or I mean just the S. I don't think we use S for arc length enough. I don't think we use arc length enough in enough problems for this equation to really truly set in. Theta is in radians, which also is kind of bizarre that radians times radius is arc length, but we just explained it. And so if I just have a small chunk of arc length, we have ds is equal to r d theta. So that's kind of the equation right here. Here's my radius, and my radius is rho, so I have ds is rho d theta, and you know what I mean. And so sweet. So that's what I have right there, and that's what I spelled out. The radius times radians, and so I just say this. I say radius times radians is something normal, is arc length, and that kind of gets me there. And we just have the conversion, or the, if this angle is real small, we just know that dx is approximately equal to ds, that arc length. Alright, hell yeah. So I should probably just fly through this, but it's good to just go over it. So we're going to put on this little bent piece of beam. Now this is the full width, this is the full height. I guess it doesn't need to be, but it doesn't matter if it is. It could be a little section of beam out of a bigger beam. I mean, that's what. But you don't need to drive it that far. This can be the full height of the beam. But it is a chunk of the beam. It's a very small chunk. And then this arc length is ds. Cool. And we're just and the cross section of the beam is shaped like a trapezoid for this problem. So we just know that, hey, and one of the principles is that there is going to be a neutral axis where a beam in bending, like these parts get compressed, the bottom gets lengthened. Now maybe you don't know where that is, you know what I mean? So, but we do know there is a location, and that's where we put our coordinate system. So before we know where that location is, we can still say, hey, there is a location where if we have compression in the top, stretching on the bottom, halfway there's going to be a point where there is no stretching, is no compression. So it's kind of like if it's 100 degrees in Florida and it's freezing in where I live, you know, maybe there's one location in between Florida and where I live that's any temperature between 0 and 100. You know what I mean? You know what I mean? So that's kind of the deal here. Cool. And there's going to be a neutral temperature. Let's say the neutral temperature is 50. You could find that location. All right, we're going to set our coordinate system, this to be y, this to be x. I guess the other thing from this, so we say that we want to put a value on this curvature, and we want to relate. So if I have a circle, like what do you need to show, what's a circle, and this is very fascinating to me. Like, how is a circle identified? It's identified by its area, it's identified by its circumference, it's identified by its diameter, it's identified by its radius. You know what I mean? So all of those would be valid. If I say the area is 20 inches, you know what I mean? It has to be a circle of only one side. There's only one circle that matches that. Same with all of these. The simplest parameter to describe a circle is a radius. And just for our problems, we're going to call that radius rho. So if I knew a value for the radius of this curve that would create a circle right there, then that describes the curve that I would have. Cool. Now, we're going to have to, at some point, divide by the radius, so I'm sure that's where they come up with this property of curvature, just so we don't have to divide by the radius. We're going to, and to get something, maybe in just like not big numbers, but just a fraction of 1. And we're going to say that curvature is 1 divided by rho. You know what I mean? So this is super sucky, the fact that we even have to use rho for radius. I think that makes derivations just like, I don't know. You see a p, you know what I mean? And you're just like, I don't know. Does that scream radius to me? Not really. And now you call 1 divided by p, which isn't p in Greek anyway. But anyway, you're calling that k, little k or whatever. I don't know what that is in Greek either. But now you're calling this a new variable. So yeah, so this makes my mind split. Like, I don't want to use it. And it feels like this is the first part of the game where I'm just like, I want to throw in the towel. No, thank you. But hell yeah. So you get curvature is 1 divided by the radius. The radius, you know, if this thing don't curve very much, radius is going to be huge. 1 divided by a huge number is a really small number. So cool. So this, is this called radius of curvature? Probably. Or I think it's just called curvature. Curvature. All right, sweet. So, what's the take-home point on this? The take-home point on this is finding, and I don't like this word either. Well, I won't use the word then. What we're trying to figure out is if this part of the curve doesn't change length, this part squishes. You know what I mean? Use words like that. This part squishes. This part like lengthens. You know what I mean? So that's what kind of happens to our curve. Like these molecules get bunched up, and these molecules get stretched out. Now, in my intro video that I just made the other day, we have to keep in mind that these molecules can't stretch out more than a change in length if it's still of 0.002 times their original length. If we have that, we might have a failure of the beam, because it'll just keep stretching and breaking, and you know, we have to keep within that limit. That's the limit that we have to keep in. Same thing for this compression. It can't be too much. But we're just showing by geometry. If I could figure out where this neutral point is, and just, you know, like for the problem in the book, they use a trapezoid. Because you'll come up with, if you did a rectangle beam, you know, the neutral axis is going to be right in the center. So you just keep that in mind. But we don't know that yet. That's something that we don't know where this neutral axis is until we start to do the proof, you know, on this next page. Okay, but from here to the next little point in the game is we want to know how much this changes length. So, and the whole idea here is strain, and I don't like that word. But strain is change in length. Stress, I think of that as like strength. I talk about steel having a strength of 58,000 psi. Strength is in psi maybe. There's two concepts, and so if you watch my intro, I don't really want to go into that. But strain is a change in length. If things start to change length, we can calculate that maybe with electronical devices that can, you know, or whatever. Just visually, it's really small. Visually, might be difficult. But with beams can actually bend very visibly, and where these molecules still don't get too much farther apart, just based on the geometry of a circle. If you have a hella big circle with that huge curvature, and then you have a beam in here, like, hey, you could have some noticeable curvature in this, you know, this depth of, you know, bending, where this length really doesn't change by much. It's still within that 0.002% change in length. Or I'm sorry, 0.2% change in length. Taking the initial length multiplied by 0.002 for steel, this is the allowable change in length. That's kind of the max change in length. I just bring that parameter up just to give you an idea of what your limits are. Okay, sweet. All right, so this derivation right here is purely based on geometry. Is that, I mean, I kind of have this accordion shape. In literature, it just says specifically that, hey, like with a homogeneous material, every steel molecule is melted or forged together in the same way. There's not going to be local discrepancies. All one material. Is that yeah, this line might change based on geometry, and that's what we find. But this line doesn't change based on you know, any given material is still going to have this neutral axis. We'll see that that's just based on geometry. But what happens is that there's what do you say? Yeah, all the molecules stretch out or compress together evenly. So if I saw hella stretch out here, I would see half of hella right there. I would see 0 at the neutral axis. So full, half, a quarter, 3/4, you know what I mean? So it's a linear, and that's going to be yes. If I see this compress, so if I have a length of, let's say, 1,000 millimeters, and I have a compression of 900 millimeters right there. Let's say it's just a real tall beam. And so at the halfway point, this line would be 950. You know what I mean? So that's kind of what I'm getting at. This line would be 925 at 3/4 of the way. At a quarter of the distance towards that line, this line would be 970 millimeters. Same thing over here. If this is 900, this has to be 1,100 millimeters. So that's kind of what we're getting at. All right, so now how I do this mathematically is see that this is a slice, this is rho, and so it's actually attached to the center of the circle. So the center of the circle is up here. And for our coordinate system, sorry I just destroyed this, is that we have, here's the x-axis, here's the y-axis, and this neutral axis is 0, 0 right there, so that's point 0, 0. And if y is the radius of the circle, so here's the axis right here, here's x, here's y. So if I put in y as the radius of the circle, this line length is going to be 0. Cool. And then initially this line length, I'm just going to, so here we go. So I'm going to say if y is rho, the length is 0. If I throw in a value of 0 for y, hey, that just gives me this original length. So if y is 0, the length is the original length, Li, for length initial. And back to our problem, we're going to say, hey, that's ds, but ds is approximately equal to dx, so I'm going to call it dx. And then even for this one, you don't even have to use the dx. You really don't. Because what we're trying to find is an equation for strain. And so now I guess I'm going to use the symbol in the term strain. Strain is change in length divided by initial length. You know what I mean? Kind of just in general. Is if I have a bar and it used to be this long and now it's shorter, well, its length decreased. You know what I mean? So I could say the strain is a negative change in length of some value divided by the initial length. So there's the initial length. Here's the change in length. I know it's negative because it's in compression, and that's just by convention. Cool. All right. So from the neutral axis, if we go up and have a positive value of y, hey, look at this. It gets crunched in. Our length decreases, so we're going to have a negative value for the strain. Change in length in this equation is just length final minus initial. So where do I have this? Yeah, so strain. And guess what? This strain as a function is going to be, so like, hey, this is the x-axis. And so this length is along the x-axis, it's dx. If I go up in a value of y, so this is where strain in the x-axis is a function of y. If I go up in a value of y, my length decreases. Cool. And strain, by definition, is change in length divided by initial length. Well, change in length is just length final minus length initial. So it's always good to write this out as strain. It makes it less hella confusing. And length final, if we're setting this equal to an equation, we just want that length as a function of y. So we're going to say length could be anything. I could be right there, that's the length. I could be this direction in y. I could be a negative y value, and my length would be over here. Okay, so I thought it was kind of hard. Like, I'm bad at, I'm getting better at being like, well, what is the equation? So here's the equation, and we'll see if this jives. So that's why I started with, if y is equal to p, and it's all the way up at that origin, starting here at y is 0, y to p is, our length is 0. There's no length at the beginning of that slice, the tip of the pizza. Anyway, and then if y is 0, hey, my length is just the initial length. Sorry, I even put dx. Like I said, we don't need it. But then if I throw in, so how do I just make those two jive? So if I throw in y is 0, I get the length. But then if I throw in a value of y is rho, I get 0. So I'm going to have this initial length minus y divided by rho. So here's my equation. If I throw in a value y is equal to rho, I'm going to have rho divided by rho, which is 1, times the initial length. And then so I have length minus initial length. Length initial minus length initial, and those cancel. And that's what I would get if I threw in L of rho, because I would be at that point. All right, hell yeah. So this is now, this equation jives. And I can even throw in negative values for y, because the length is going to increase. The length here is going to be more than the length initial, so we have length initial minus a minus y value. So that's going to turn that into an addition, length plus an additional length. So if I went negative rho, I would have negative rho divided by rho. If y is negative rho, I'm going to have negative rho divided by rho. That's going to be negative 1 times the length. And then I have this minus a negative. So I would have the length plus the length. So yes, if I go a distance rho this direction, this length is going to be twice. So, and it's just a triangle, so you can see this wedge. This length doubles, this doubles. Cool. All right, hell yeah. And so when we throw this equation for our length as a function of y, and that's the length final minus length initial. Length initial we're just calling L. So this length final is L minus y divided by rho L. L minus y divided by rho L. So that's length final. And then we're subtracting length initial, minus L. And then dividing by length initial. And again, strain is change in length divided by length. And if you took change in length divided by initial length times 100%, it would make sense. It's just like, hey, if this is my initial length, and let's say I stretch it out to there. It looks like I doubled it. You know what I mean? So so this was my initial length. I changed my length by L naught. And so I'm going to have L naught divided by L naught times 100. And I just increased my length by 100%. Hell yeah. So even on here, if I threw in a value, so we can check our equation. We're going to get an equation for strain in a sec. We can check our equation by throwing in a value of negative rho. If we throw in a value of negative rho, what happened to our length? It doubled. So we have a change in length of 2L minus the initial length, and that's going to be a change in length of L. Strain is change in length divided by the initial length, so I have L divided by L. Strain should be 1 or 100%. It's very good to think of strain as a percentage. I don't like the word strain because it should be called stretch, or you know what I mean. Anyway, I think stretch is a good term to call strain. You can call it strain, but just think stretch in your head, or just keeps calling it stretch as long as you want. All right, hell yeah. And when we do that, a lot of stuff cancels. We have L minus L. Those two L's cancel. And then we have this as a function of L divided by L. So those L's cancel. And now we're just left with strain as a function of y. So I'm going to throw in any y value. And it's going to give me the strain. And what was strain? Think of it as a percent change in length. Strain is change in length over initial length. It's the fractional change in length. But I think fractional change in length is harder. You know, when I do sines and cosines, I think of sine theta, cosine theta as a percent of the hypotenuse, even though it's a fraction of the hypotenuse. It's a side opposite divided by the hypotenuse. That is a fractional component of the hypotenuse. If the opposite is equal to the hypotenuse, you have a 1-to-1. You have a fraction of 1, which would be 100%. Of the hypotenuse, you know what I mean? So, but yeah, I think that is tricky when working with fractional numbers. You know what I mean? Strain is a fraction of the original length. Cool. And so, and at this point of the game, like, you know what I mean? The negatives don't mean anything. They just make sense to our axes. We chose this is our x-axis, our y-axis going towards the center of our circle up. We're saying that a smiley face is a positive curvature. You know what I mean? And we do that, and so one reason you can see this is like, hey, my y value is going to be a positive rho. You know what I mean? If I did a curvature like this of a beam, I'm still going to put the up direction as my y-axis. This is my x-axis. But guess what? The radius is a negative So y would be a negative rho. So that's how this gives you a negative curvature. So curvature of this equation would be 1 over rho. In this equation, I would have curvature is 1 divided by negative whatever that value is. And so this would give me a negative curvature value. And so that's how this is a positive. That's how, you know what I mean? I don't think anyone's going to explain that, but I just found a way to explain it to myself. If I always choose the x-axis towards the right, the y-axis is up, and you know what I mean. Then, and the curvature is a radius, but the radius is still on this y-axis. And if it's like this, hey, I'm going to throw in a positive value for the radius, positive rho. All right, booyah. So we have our strain equation, and again, what did I say? Is like, well, we have two equations here. So our strain equation was just negative y divided by rho. So that's what we have here, negative y divided by rho. But we're going to say 1 over rho is that curvature. So our strain equation is negative ky. But I did say if rho is negative, if my y value is negative rho, I'm going to have negative rho divided by rho. I'm going to have rho divided by rho, that's 1. So my strain is 1 if I go down here, and that's what I said. This length doubles, which means the change in length started at this initial length, and then increased L. So that's the change in length is L, initial length is L. That's an increase of 100%. And so that's the take-home point on strain. That's where you can really feel like you're mastering it, when you're just like, hell yeah, it's a percentage increase from the original length. Booyah. All right, so now we have to, this is where definitely watch my intro to material mechanics. We don't go over how, well, I mean, just briefly. You know what I mean? There's two different ways to measure whether something is going to fail, or there's two different ways to figure out how much force is on some sort of material that's holding strength. I'm going to have a 1 meter bar that's 100 millimeters. For steel, the strain is 0.002. That means that if I have 1,000 millimeters, I can stretch it 2 millimeters. Before bad things happen. Basically just becomes plastic, but you can set that as a limit of maybe failure too. You know what I mean? Like, hey, we don't want things to go plastic because that's when it could catastrophically fail. Okay, so let's say I pull on a 1 meter bar and I stretch it 1 millimeter. You know what I mean? What does that mean? So sorry, it's easier, just one inch. 1 square inch steel bar. Steel has a strength of 58,000 pounds per square inch. I can put that much pressure in any chunk of steel that I get. And so if I have a bar with an area of 1 square inch, 1 inch by 1 inch steel bar, pretty heavy duty, I can put 58,000 pounds. I could hoist a semi-truck with it. And a 1 meter steel bar is going to stretch 2 millimeters if I do put 58,000 pounds on it. And so then the reverse is true. If I only stretch the steel bar by some means, using force, and I can measure that I stretched it 1 millimeter, that means that I stretched it half of 58,000 or 29,000 pounds. So I can use that. I can say that a change in length matches a given, like, PSI, you know what I mean? Like, if the max strength is 58,000, that means there's 58,000 pounds of, pressure on the surface area. And if I know the surface area, that directly links to pounds. So that's where it's just like, if I use a 1 inch rod of steel, 58,000 pounds, and I can stretch it 2 millimeters. Stretch it 1 millimeter, that's 29,000 pounds. And anywhere in between, a fraction of a millimeter will line up linearly with a certain amount of pounds that I put on that. But I think that is one of the harder take-homes of, like, this strain is giving you. It's another way to say, like, pounds of force. Even though both strain are wrapped up in bizarre little, this is a fraction. It's a percent of the change in length. It's not the new length itself. This number doesn't give you that 1,000 to like 2 millimeters. It gives you the percent change in length and that is the bizarre thing, because like steel, the max strain you can have is 0.002. I said if I have 1,000 millimeters, I can stretch it a max of 2 millimeters. Well, going back to how much in this equation, I changed its length by 2 millimeters. Its initial length was 1,000, so that's a value of 0.002. I said I could stretch it only 1 millimeter. That would be a change in length of 1. Initial length is 1,000. That's going to be 0.001. I can't change its length by 3 millimeters. Let's say, bad things happen at that point. So I can't use 0.003. So 0.002 is the extreme limit. But this is a moving value. I can say that's a stationary value if that's the max. So strain for steel is 0.002. But if I'm just out there and I'm stretching some steel, maybe it's 0.001, 0.0005, like half of 0.001. Cool. And all of those terms are going to line up with some sort of load that's actually trying to stretch that beam. And the material itself doesn't know the shape or how much material you have. So we talk about load in pressure, PSI. And so that's the, I guess just using words to explain that this change in length is equal to the pounds of load. So even though this doesn't say change in length and this doesn't say pounds of load, this says pounds per square inch. So it's pounds of like per, what size of bar are you using? Then you have load. So this is force that you're putting on a bar. This is change in length of the bar. They're just in universal terms. This is a material property of steel. It can change its length by 0.002 given your initial length. This can withstand a PSI pressure of 58,000. So we do have two max values, 0.002 and 58,000 for steel. And so those are the max values. If I only change its length by, half of the max, or, if I only strain this thing halfway, the change in length divided by the initial length is only 0.001, I'm only going to have half of that max. And so this is a linear relationship. And so this is the equation of a line. There is no difference between this equation than y is equal to mx plus b. This equation just starts at the origin. Hella goes steep, but it doesn't have a b. b is the y-intercept of 0. So this equation is just y is equal to mx, and then we just have a slope. More or less, this is saying, hey, I've got 4 apples, and I could make, or I could make 2 pies if I had 4 apples. And I do have 4 apples, so this conversion right here is 1/2. So it's like if I have this many, pies, I can make this many. If I have this many apples, I can make this many pies. And so the number of apples, if you count apples, you're going to be like, that's 3 apples. And if I count pies, I'm going to be like, that's 2 pies. So 4 apples, 2 pies. These are not the same thing. Same thing here. Change in length and force are not the same. But we can have an equation that relates them. You're like, hey, every 4 apples I get, I can make 2 apple pies. And so, it's just, I think there needs to be more discussion on equations that relate to different things. But this is classic, is that I can measure, if I see that bar and it's stretched out, I know the force on it. If I measure the force on it with a meter, then I know how much it's stretched out. You know what I mean? So that's that equation. And the stretching out is a hella small number. So right back here, this number is hella tiny. This number is decently big. And so how do you take a tiny number that's less than 1? You must have to multiply it by a giant number. It's not too giant, but that's where this constant comes in, and it's modulus of elasticity, or modulus, it's also the rigidity of a structure, depending on whether you think a big value is a big value is stiff and a low value is elastic. All right, hell yeah. So now we have, we solve for this strain equation, and we're just plugging it into here. This elasticity is a constant. So this is where we take some steel, pull on it, see it's changed in length. We can get that value for strain, and we can know how much load that we put on it. Change in length and force. That's kind of what you're doing here. And then you're trying to get an equation that relates change in length and force, and we see a linear relationship. So our slope is just E. You know what I mean? Because this is load, force, this is change in length, but this ain't the graph that's universal. It's stress, which is force divided by area, and this is strain, which is change in length divided by length. Cool. Like a force change in length graph would be different for every specimen. Like a 1-inch chunk of steel compared to a little bolt will have still a linear relationship, just different values. Where if you take the force divided by area and the change in length divided by this length, you will get the same graph every time. So that's kind of the take-home point on that. But still, equation of a line. All right, we need to move on. Cool. So we're going to take this equation and put it into here. And then yeah, so that's all we do. We just take and this is stress is equal to E, and then we're going to use this, negative Ky. We're just going to rearrange it. Stress is equal to negative Key. This stress is still in, the PSI is still what we see kind of on the face of, well, it's going to be all throughout there, yeah. So in the middle, there's no change in length, so there's going to be no pressure. You know what I mean? It would be the same thing. You take a chunk of steel, put it in the bottom of an ocean, there's pressure all around it. Where right in the middle, no pressure ever in a beam bending, but up here, right at the crunching point or the stretching point, there's going to be hella pressure. And it's based on this Y. So if I throw in a positive value of Y, the pressure in compression is always should be a negative pounds per square inch. I should have a negative PSI. And so that's what we have, a positive Y value. We're going to have this negative makes a negative PSI. This is a constant, just a number. Our K, given this, had positive curvature, so K is positive. But all of these, even though this equation has a negative, it's always good to be like, okay, there's the negative. K, though, is positive for this curvature. For a problem like that, curvature is negative. This would be negative. E is a constant slope. Our equation is this. If our graph showed something the other way and we were in Bizarro world, but we're in geometry world where everything should be in this first quadrant. But hell yeah, so our slope is going to be positive. So we have a positive curvature, positive slope, and I just said if we throw in a positive value for Y, we're going to get a negative PSI, a negative pressure. Where if we put in a negative value for Y, we're going to be down here in that tension, and so that's going to be a positive PSI. And so if I throw in a negative value of Y, negative, that's going to be a positive tension. All right, hell yeah. So I'm running low on juice. I need to take a break too. All right, hell yeah. So we're back, and we're going to see what's on the next page. So yeah, this is cool. So I guess the foreshadow is if we know... Well, two things. Like, you can use both of these equations synonymously. Because, yeah, this is fascinating to me even. um, well, if we know the psi, we know the load right there in there. You know, we know the internal pressures. Like if I pull on this pen, I know that there's tension in the pen. Even though this is, F equals ma, we're not accelerating this pen with a force. I'm putting equal and opposite forces on here, but it's drastically different than there's no force. Internally, now there's forces. So, all these molecules are getting compressed. And even when I pull on this pen, it does change in length based on, the strain equation. Or just the fact that everything is elastic. So, you put a force on something, it's going to change length linearly. Put 5 pounds of force, the pen changed molecularly this much. Put 10 pounds of force, it doubled, that change in length, it doubled. So that's where that strain value, change in length divided by the initial length. And it doesn't even matter that it's divided by the initial length. Again, 5 pounds of force on this pen, molecularly it changed length that much, let's say. And then if I put 10 pounds, that change in length doubled. Cool. It's only the fact that we take that change in length and divide it by a length. Now we actually have a material property for that material, plastic steel. Cool. And then same thing for figuring out what the PSI. PSI is the surface area, the cross-sectional cut, that area divided by the force. And then, and if this pen broke at a certain pressure, at a certain tension, then we would say, hey, this material can only get up to that PSI. All right, sweet. I was thinking like, hey, if we know the strain, we know the force as well. But this strain, we're using geometry to find the change in length. So this strain component, this equation, is our input value of where we are on that beam. So if I'm up at that high, the outer reaches, my strain is going to be the largest. My change in length is going to be the largest, and that's going to, this equation says that that's related to the force, internal forces. So stress is related to strain just by a constant, just because we set up tests, and we find that slope. All right. So we're going to take a little chunk of that beam, and here's the side cross section. And so when we cut that chunk of beam, just a little bit of area, we have pressure. So this is in PSI. It is a pressure. That's the stress. And we had that equation, like where'd it go? So right here. So here's our equation for the strain, or the strength of the material. I call it strength, but stress, I call it strength, stress and strength, and then strain I call stretch. Oh, I don't even know what the hell I just said. So strain I like to think of as stretch, and I just say stretch a lot. So then I don't like the words stress and strain, they sound like the same things. So this is stress, sigma, this is in PSI. I like to think of it as the strength of the material. If you have a car tire, you pump it up to 30 psi, that's the strength. It's going to flat spot that many square inches based on how many pounds that you're putting on it. Same thing with a railroad car. The railroad steel is really high strength, but still it flat spots based on the strength of the steel. If I same thing with like if you took a like a steel point, like a carbide bit point, or like a like a punch, to set a hole into steel. Well, the steel is pretty soft, it actually gives. But let's say you tried to take that same, well, let's say it's a cheap one too, and you try to make a hole into diamond. And so you put a hell of a lot of force on that punch, or just that starter hole. Well, that tip of that steel is just going to flatten out it's gonna turn into that, because steel can only take so much psi, and so if this molecule can only take, each molecule can only take a certain amount before the molecules start to move like that. So your point like that just turned into a point like that by putting force on it. All right, hell yeah. So let's see. Yeah, there's a fundamental here we need to go over. All right, hell yeah. So we're actually gonna have to go over go over the first. I think it's called the first principle. The moment's the second principle. But anyway, when we cut this cross section away, like and the take home of this video is like you have a beam and then you bend it by applying some sort of moment. And even like what's a moment? Well, just think of a moment as like a force right there and a force right there. See, a moment is still a force times distance. It's just that these distances are just hella close. So we're just going to have a very small change in distance, but still it's going to be a force that direction, a force that direction. You know, it's like a torque. It's just that the distance between these forces is basically non-existent, and so we're just applying a direct moment. When we do that, it's just fascinating that we don't get any axial loads, but we do get internal loads based on just kind of what we talked about. Just from geometry, like, hey, this gets crunched, we see a change in length, so we go the direction of strain, we see that change in length. That change in length must indicate compression. This change in length down here, it must indicate tension. And those changes in length are internal forces. So this is a force that's causing, so just on kind of both of these, I would have a force that way and a force that way. And there is some sort of neutral axis. We talked about that. Where there's a point where there is no stretching. So just based on the strain equation, if I see change in length is 0, there is no force right here. Okay, so this is just a force diagram where we have equal forces this way, equal forces that way. And what we do is we use and then this is our origin, so we have our y and our x, and now we're just going to look at this face right here. So this is the x direction, this is upward is the y direction, and we're going to turn this face sideways. And that means that we have forces on this face, and these forces, the forces on these face are going to be the pressure times the area. Because pressure is in pounds per inch squared, area is in inches. And those are going to give us a force and pressure. So that's what I would have right here. So before we do a derivative, I'm just going to say force is equal to that stress times area. Force is equal to strength times area. And now I can take a small little chunk. So I know, like right on, and then so I've already, and what we haven't talked about yet, and what we're going to go over, that's the next thing, is I've set my axis at the neutral axis. Again, I know that there is a neutral axis, I just don't know where it is. So when we set this axis, I'm going to say that, hey, this little chunk of area has that stress on it, which is a function of, its position y. So we have that equation. That's going to be this equation right here. And that stress times that little chunk of area. So now we can do a derivative. So a little tiny little force coming out of the thing is equal to the stress times the little area. I think the hardest things with derivative is just like, what gets a d? Well, you know what I mean? Like this stress is a number. It's going to be that value. That PSI doesn't change just because we have a tinier area. You know what I mean? And so this value is unchanging, but the area we're saying is real small, and then we're getting a small force. So little dF is equal to sigma dA, strength dA, stress dA. And then when we integrate this, so we're going to integrate this, and this is going to, integration sign is sum of the forces. So sum of the forces when we integrate from, this point to this point. And obviously we're going to integrate left to right first and then up and down, but whatever. We're symmetric left to right. I'm not going to go over that for this video because I want to do this a few times. But anyway, and so when we sum the force, that's going to give us the sum of the forces. So when we're down here, this value of y is a negative value of y, and so the stress is going to be a negative value of y. And so we come to our equation. We're going to have negative. Curvature is positive. This is the slope of the stress-strain curve. We talked about that. That's positive. Let's say our value of y is negative. Cool. That's going to give me a positive stress. That's going to give me a positive. And then the area, just by sign convention, if this is the x face, the dA is going to be a positive area. So come in here, I got a positive area. I have a positive PSI. That's going to give me a positive force. But if I'm up here above the y-axis, above the origin, I'm going to have, this is going to be negative, curvature is positive, E is positive, and I'm going to be a positive y. That's going to give me a net negative, like we say, we're crunching, we're compressing, and that's going to give me a negative PSI for the pressure, for the stress, for the strength of the material. Negative strength, negative pressure, negative stress. Those are probably the three words I would use. And so for our little equation of that force up there, so force, let's see what its sign is going to be. We're going to get a negative for stress, and our little element area is pointing in the x direction. That's going to be a positive area. And so, hell yeah, negative and a positive, and I get a negative force. So all the forces above here are going to be negative in compression, and all the forces down here are going to be positive in tension. And we knew that, but what we did is we just set up a derivative. So we have, but from the free body diagram, we know the sum of those forces on that face have to be 0. We know the forces going that way have to equal the force going that way. We do generate a moment. For sure we generate a moment. But the sum of the forces have to be 0. So here was our integral. So we have the sum of the forces equals 0 equals the integral of df. And what we were saying, anytime you're doing an integral, go back to what's the equation? Force is equal to strength times area. This is going to be force in pounds. This is pounds per inch squared, and area is an inch squared. If you did it in newtons, it would be newtons is equal to pascals. Newtons is equal to Newton meter squared times meter squared. A pascal is a Newton per meter squared. And then, so your units cancel. Your units are good here. So and then again, derivative of the force, just a small little force is that number, pressure times a little bit of area. And when we sum all those little areas up, that's going to be the integral. So sum of the forces, same thing over here, is just like, hey, sum of the forces in the x direction are 0. Sum of these forces in the x direction is going to be equal to the integral of sigma x as a function of y dA. And again, I'm not going to go over the integration. I'm going to do that for another video because I really just need to kick this one out. But I do spend a lot of time on the actual integrating just to make sure. And I think and I apologize I'm not going into a longer video. I just don't have it in me. I just want to get done with this and finish. But hell yeah, it's very important to actually do the integrals. Set this up. This is dA. This is a double integral. I like to do a little slice. See, that's where it's just not going to make sense if I go over it fast. I don't like to do a little box. I like to do a little slice. So I'm going to call that dx. It's a distance x from the origin. And so for my first integral, it's going to be x is equal to, and I got to get this equation as a function of x. This equation is a line. This equation is y is equal to mx plus b. just solve it for x. Cool, that's going to be x equation 1. This is y is equal to mx plus b. Cool, just solve that for x2 is equal to, you know what I mean, something. So I have x in terms of something something y, x in something something y. That's integrating from there to there. What that gives you, all that gives you, like when you have a trapezoid, so I guess I am going over the integration. Like, yeah, so I'm setting that up. After integrating just that first one sideways, it just takes this trapezoid and makes it that, you know what I mean? So it's just this. Now you have this is x is equal to something something. It's the equation of this line. And the fact that it's sideways makes it super messed up, but it's the same thing as saying, hey, if this is my positive coordinate, like, it's the same thing as doing, well, this is like really hard to, yeah, it's the same thing as this line is that line, and then slope down to, ooh, why is this so difficult? What? I mean, if this is the x-axis, y-axis, okay, yeah, there you go. Okay, yeah, I was totally messed up. If this is, well, y-axis, holy Toledo. Yo, why is this so hard? Yeah, oh yeah, this is mind-numbing. So the first thing I want to do is just flip the axis this way, just on its side, just tip it over. You know, I can visually see that. And so, yeah, let's say this is 1, this is 2, and then this is 1. So we actually have a trapezoid, and then when I tip it over, this is going to be 2, and this is going to slope down to 1. There you go. And then I'm going to flip it to get it into this quadrant. So this is going to be x, y, and this is going to be, this is still going to be 2. This is going to be like that. Whew. Brutal. But yeah, how hard is that? You know what I mean? And all we did there is just say, hey, we got a function of x is something something. You know what I mean? That's the same thing as this is an equation y is equal to mx plus b. You know what I mean? Y is equal to something x. We can just visually see that that's that, and y is the height of that line. Well, it's no difference than sideways. That's the height of that line, and so that's getting x. So that first derivative just gives you that equation. It takes this and then just puts it all on one side and gets that equation as a function of x. Cool. The second derivative of that, so this is the dx part, the second derivative is, you know, just, that's the simple, it's just y is this height to y is that height. You know what I mean? So it's just, and our coordinate system's in the middle, so we call this C1 and this C2. So this is C1 to C2, and that C1 is negative value, it's below the origin. Okay, but I think we're getting carried away. I'm just showing you, because the crazy thing about this is like, hey, we said this equation was equal to 0. Cool. So this gave us the sum of the forces, and I'm going to get this equation. So that PSI in the axial direction as a function of y, because we're going, you know, we're going up this arc and down this arc. So hopefully that can be the hardest part, is just like, I don't like this. I don't like the fact that this is stress. I don't like the fact that it's in PSI. I don't like the fact that it's axial in the x direction, and then you have this other term because it's a function of y. Like, you know what I mean? You have the pressure along this axis, and then so when we're on the face of it, you have a face pressure, and that's going to be a component of that force, because force is pressure times area. I don't like that it changes while I go up the y, but that's the whole point of this. We started with geometry, with this strain, which is a horrible term, but it's change in length divided by the total length. If I notice a change in length getting shorter, hell yeah, I know that's compression in PSI, and basically, you know, overshoot PSI and just say, hell yeah, that's a force. That's a compressive force. And so that's where we're at. We're summing the forces. And But yeah. So this equation is the curvature EY, and we have sum of the forces in the x direction is 0 is equal to this integral df in the x direction is equal to the integral sigma x y dA. So now we can throw in this value sigma x of y into this equation, and we know this is all equal to 0. Sum of the forces is equal to the integration of negative KEY dA. Cool. We just said that if we did the dx dy, we already did the dx, and that's going to give us, if you do this in two parts, this is just the range of x. I'll just do that, x initial, x final, and this is y initial, y final. Dx just becomes x, and you just get the equation of that line, of that profile. After you do that integral, then you can integrate from the y value, this negative c1 to c2. Holy hell. Yeah, see, I'm explaining more than the textbooks, because the textbooks, let's see what the textbooks do. The textbooks say, hey, sum of the forces are 0. Don't get too carried away. We're going to take out the constants, curvature E, and then we're going to do an integral just over area and say this is just y dA. Cool. And then we're going to say that's equal to 0. These are constants. You can divide those away, and then you're just left with this, with which you have to like talk out. Like this wasn't like, oh, aha, but to them, to the textbook writers, it was. It says that the moment of area, that's just where, like, anytime that you have moment of area, think moment of force. Because let's say I have a 1-inch chunk of area there, and then no area. So I have a 1-inch chunk of area there. This is going to be my neutral axis. A 1-inch chunk of area there and a 1-inch chunk of area there. And this is a plate where these are heavy chunks of steel, and then it's kind of on a framework where, like, this is hollow. There's no steel here, but I can still support this. I could put something to support. So just even visually, where would I put the support? I don't know. You know what I mean? You would put it maybe right there. You're trying to balance that. So if you think of if these are weights, or forces, that's and where we're trying to balance it is the same as this. This is moment of force. The reason why this balances, because the tricky thing with moment of area. So let's do this one again. 1, 2, 3, 4, 5. Is what I mean? If you thought the center of this was just half the area on one side, half the area on the other side, you would say, hey, that would be half the area is there. There's 1.5, and half the area is there. And that's where you can get confused with where the center of something is. And so the reason you can't balance something right there, if this was 1 pound and this was 1 pound and this was 1 pound, these were 3 masses on kind of a massless, foam little table where all your weight's right there, there, and there. You probably can't support it there. Just even visually, you'll probably be out there somewhere. Like we're very intuitive of like balancing weight, but it's because it's a moment. So this is some little area, and this is a distance away. So we call a moment a quantity times a distance. Cool. This is the definition of a moment. Whether it's some sort of mass, it could be kilograms times a distance. You know what I mean? That could be a first moment of mass. And first moment of mass is very similar to first moment of force. because it just means that we do have mass out here, and we do have the meta distance. It just means that we have an Earth underneath us, and there is a downward attraction, and so we have the only reason that this is the balance point is first moment. Force times distance is first moment of force. We have a quantity of a force. It's a distance of way. That's called the moment. But it's the first moment of force. So that's how you say that. And this is the first moment of area. It's just bizarre to be like, ooh, I have some area, and it's like, this is the x direction, let's say. Ooh, so it's we have some area. We got a value on area, and it's in that direction. It's pointing that way. And we're going to have some sort of distance away from it. So if this is the y-axis, we're going to have a negative distance there. And so, and you know, this is a vector, you know what I mean? So we could say this is first moment of area. I think it's q. I think that's what first moment of area is. And so we could say vector q is going to be, it's usually r cross f, so it would be r cross dA. So we would have r cross, we'll just, r cross A? That's how you do it. So r cross A is that first moment. Just like moment as a vector is r cross f. Cool. And so perpendicular distances, you know what I mean? You really don't need to do the vector thing. It's just going to be multiplication. Moment is just distance r times f, or rd. Or I mean FD, however you're going to do that. So first moment is just area times distance. So we have a little area, and we have a distance to that area. Cool. Integration just means that, hey, like, if I have this chunk of area, like, well, could I measure from the middle? Well, yeah, if I measure from the middle, I should be measuring just that little strip of area. So that's where you have to do the integral, even though if you take all this area and then multiply it by the center, for first moments, you'll be just fine. Second moments, hell no. I mean, if you're going to square the distance, like this area out here is way more purchased than the area right here. But for moments, like just the fact that if you're trying to balance a teeter-totter, twice as heavy adult and half heavy kid, equal distance? Hell no. So, but if you do the same teeter-totter, if this is half the distance, twice as heavy adult, same distance, half as heavy kid, this works out. So you know what I mean? Even though this adult has mass over there and mass right there, and they're different distances, but their center, you know what I mean? So that's where first moment, you know what I mean? There's the summation. I'm not going to go over that. But yeah, people hate, especially engineers, they hate integrals. I don't know. Like, you just want to graduate without ever doing an integral. Calculus is just a class to pass. But no, it's kind of fascinating. I'm kind of diving into integrals as much as possible. It's the setup that gets you. You know what I mean? No one teaches the setup. And I know that because, like, I've been doing it this way. It's like you don't start with a chunk of area. You know what I mean? Let's just start with a little dx length, you know what I mean? Because we got to integrate one direction, and if you integrate one direction, you get the equation of a line, you know what I mean? So if you integrate a little dx, you get a line. You integrate again, then you get a slice, and you get an area. Integrate again, you get still a slice, but once you integrate that slice, you get a volume. All right, so what next? Oh yeah, that's what I hated about this. They were just like, the proof ends right there. It's just like, hey, voila. And so if this is equal to 0, it says the moment is that if I have some area above this axis, the distance away, the leverage of that moment is good to talk about, like leverage too. The area up there is leveraging the area down here. Now again, it's not half the area, because if I did half the area, or or yeah, go back to this one. If I did half the area on this one has way more leverage. Because even I was going to say the opposite. Even on here, if you did half the area, oh, I don't know. Yeah, that's interesting. It's going to be really close for a trapezoid. But if you did have half the area, this area would have more leverage. And so you'd be lopsided. So you would actually have to increase the centroid a little higher. And hopefully I said that right. If I said it totally wrong, I apologize. But I'm going to do that tomorrow. It'll be a good one to do. But hell yeah, right here, hell no, you'd balance it right there. And because where you would balance it, there would be no net torque. And so I could say the sum of the moments where I balance it is 0. But if I have like 1 pound down, 1 pound down, 1 pound down, and then balancing it is actually supporting it. So I'm going to have 3 pounds up where I balance this, you know what I mean? And so then some of the forces can be in any direction you want them to. If there's no external torque at that center, there's no torque anywhere. You know what I mean? So then I could take this, I'm just going to call it point A. I could say some of the moments about A is 0. And then I'm just going to call these distances 1. So this is 1, so we have half of 1. So I have a half. So this moment's going to be a negative a half times 1. This is going to be 1, 2.5. It's going to be plus 2.5 times 3. These are going to be negative, so we got minus is going to be, I shouldn't have done halves, but whatever. 1, 2, 3. This is going to be 3.5. So 3.5 times 1. And this one's going to be 1, 2, 3, 4. 4.5. So we got minus 4.5 times 1. What did we do? So we have negative 0.5 plus, this is going to be 3 times 2.5. 2 is 4 halves plus a half. That's going to be 5 halves times 3. That's going to be 15 halves. Okay, I think we're going to work in halves. So we have negative 1 half plus 15 halves minus, this is going to be 7 halves minus 9 halves. Cool. So now you just add them up like oranges. We got 15. For the negatives, we got 7 and 8. That's negative 17 plus 15. So we got negative 2 halves. Cool. Oh, this one worked out pretty nice. All right, hell yeah. So, oh, my bad. We don't know this distance. Yeah, I just put it right there in the center. No. We don't know that. So let's hella start over. And let's not call them halves. So we're gonna say each of these distance is, each square is 2. It's a 2 by 2. So this is gonna be a negative 1. So we have a negative moment, a distance of 1, weight of 1 pound. This is going to be a positive. We don't know where it is, it's x, but we have 3. And then we have negative, we got 1, 2, 3, 4, 5, 6, 7. So minus 7 times 1, and this is going to be 2, 4, 6, 8, 9. And so minus 9 times 1. All right, brutal. So I see a negative 1 plus 3x, 7 minus 9. I want to do this all in one go. So 8 minus 9, negative 17. So we have 3x minus 17. And those are all the moments, and they just have to be equal to 0. So we have 3x is equal to 17. X is equal to 17 thirds. I don't even know what that is. All All right, 5.66. So if these are each 2, we're going to go 2, 4, 5. So 5 is right in the middle, and we're going to go just a little bit more. So you can see that these two areas are actually all on that side. And this area is lone over there, but it's generating a much more moment. So the center of this is not where half the area is over there and half the area is over there. I just wanted to go over that because while I was going through that, I made that mistake. You know what I mean? And it's good. I think you should explore that. I think the mind really wants to explore, you know, like stuff like that. It's just like, hey, why is that the case? I need to work on that and work on proofs. So sweet. So I think we thoroughly did it, is that yes, and there's no difference between area, moment of area, the fact that you have some area out there, that area has weight, it's a property, it has, you know what I mean, it's like there's area there, there's no area there. And this area times that distance is effectively the same thing as saying mass times distance. And it's no different than making those steel plates that really don't have too much volume, but they do have a lot of weight, and they do have area. You know what I mean? So the area of those is, area is proportional to the force. So I guess that, yeah. So it's good to see what is proportional. So yeah. So this integral y dA is equal to 0 is the same thing as the integral of y. Well, yes, sigma dA was force. Yeah, so I think that's the bizarre thing. Oh, yeah, okay, I get it. Yeah, the fact that sigma is the pressure, but it is a function of y, and it does have, you know, the equation for that is a function of y. And so, sure, force is synonymous, like the moment of force is, yeah, it's saying the same thing. Because we have strain in these, we're going to have forces, crunching forces and stretching forces. And the force is the pressure on those little chunks of area. So each of those will have a force attributed to them. And they're going to generate, what are they going to do? I'm just going to say it because I don't think it's super clear. So the moments of these forces are going to, well, the moments of these forces are going to be net zero. But the neutral axis, oh damn it, I actually don't see that one. All right, shoot. I need to work on this one more. No, this is just a property that fell out of this equation. You know what I mean? Because we see this moment of area, there's a positive area above the neutral axis and negative area below the neutral axis, and this spells it out. It says if we have an axis that we chose, and we take that area and multiply it by the distance away, and do the same for the area that's below the neutral axis, which will have negative, you know, it's the leverage of that area times its distance, so it's the moment of that area summed, and the negative moments, these is positive moments, those are gonna cancel, and that point is going to be the neutral axis. So it says if we're on the neutral axis, the moments of those areas will be zero. Because if we do it with force, that's not the case. Because I got forces going this way, and I got forces going that way. So the sum of the moments of this, no matter where we're at, neutral axis over here, over there, is hella equal to this bending moment. So I'm totally glad I didn't destroy it on that. But that's where it's just like, this stuff is so complicated. For me, this is just hella complicated. And so I'm just trying to find ways to make it approachable or easy. By talking nonstop, I don't know if that helps. People have said it has, and I think it does. I'm sure there's just a whole... It would be nice to get better. But like I said, I did this in the last couple days even, and each day I redo it, and I was just like, I'm not going to finish today without going over it. You know what I mean? So today was the day, and I think we're doing fairly decent. But yes, there is a moment here, but it was just that what fell out of this was this, and this was supposed to be the aha. And it's very even difficult for me to even see. I mean, the centroid is equal to YdA divided by dA, which is the moment of area, Q, divided by the area. You know what I mean? And even though this looks like area times y, well, it's the summation of, it's the weighted value. If I have an area over here a long distance away, hey, that gets a bigger number. And then summing them, and then dividing by the total areas that I have, that's going to give me the distance. And it's the equivalent distance. If you do it with weights, if I have a mass there, and a mass there, and I try to balance these, it's the forces are down. Forces are down, and then the balance point is up. And and obviously that's going to be each of those. But then this distance can vary. So that's going to be and then the moments, and then the sum of the moments are going to be the same everywhere. It doesn't matter if I sum the moments there. Things not going to rotate, so there is no external torque. It's just the fact that, where is this distance to cause that? But that's the same thing with this. I have a chunk of area there. Put the areas on a string. I got a chunk of area there and a chunk of area there. And if I say, hey, this, and it doesn't matter where this, so that's cool. It's always good to be like, hey, let's say this is the x-axis and this is the y-axis. You know what I mean? Sorry, the y-axis, even though axis is kind of tilted. And because this problem is vertical, this is a horizontal problem. But it's saying, hey, where, what is this saying? Alright, holy hell, I almost don't believe this equation. You know what I mean? So let's set this up. We're going to do hashes. So I have, I'm going to put a weight at 2. And then we're going to go over here and a weight there and a weight there. This is a distance of 2, 3, 4, 5, and 6. So this says, and these areas have 1. So we're saying the summation of these. So we have 2 times 1 is 2, plus 5, plus 6, and then we're going to divide. Yeah, so I think I'm missing something here. I better stop the video. Damn it. You know what I mean? Yeah, why is the centroid equation... Am I missing something on the centroid equation? I mean, because the centroid equation... Do you have to start at a neutral axis? Is that what that's saying? Don't know. Alright, hell yeah. I'm so glad I couldn't find it in the books, but I'm just so glad. Yeah, if we're starting here, what this says is, and this is the y direction, it says from right here, we're going to generate a moment. We're not saying the moment is 0, but we have 2, and this is a mass of 1, and so we're going to take those, and 2 plus 5 plus 6, and then divide by the area is 2 plus 5 plus 6. And that gives us a moment. Oh, no, I better look this one up. It's not making sense no more. Alright, hell yeah. I'm glad I just lost my mind right there. So statics has the center of mass. And man, I just made a little error. You know what I mean? I was saying that these are the distances. These are the masses. So if we're relating this, this is the distance times... the area. So if I'm saying this has an area of 1, area of 1, area of 1, it's the distance. So let's redo this. So it's the distance. 2 is the distance. Area is 1 plus 5 is the distance. Area is 1 plus 6 is the distance. Area is 1 divided by the sum of the areas. Well, that's going to be 1 plus 1 plus 1. Sorry about that. And I was just like, holy Toledo. And it's just so fascinating, though, on these, is that you can't factor out this 1. This is not the same as, because we get, this is not the same as 1 plus 1. Yeah, let's slow down. So this is not the same as 1 plus 1 plus 1 times 2 plus 5 plus 6. So that's the take home. It's bizarre, like because it's a weighted average of each of these. It's not this, and I think it is good to do some sort of proof like that, just to be like, hey, this isn't this. You know what I mean? So, because else you would just have the distances these were. But cool. And so that's going to be the leverage. Well, no. This is the center of mass, and it's the equivalent of having, if these are forces down, to balance them up by putting them right there. And so we get 2 plus 5. What is this? 11, 12, 13 thirds. So 13 divided by 3 is 4.3. So we'd be at 2, 4. So right about there. Does that look about right? Hell yeah. And it's just fascinating. Again, you have twice the area over here as you do on this side, but this is leveraged of that area. All right, booyah. And, oh yeah. And so what we did is this equation, we found the center by taking this moment. Yeah, this part is the moment of area. But then if you divide it by the area, you get that centroid. But if I now know the center and I want to just take this, I want to sum this area. This area is going to be a positive distance. This area is going to be a negative distance. And so those will sum to 0. So if I start at the centroid, this integration of y dA is equal to 0. I do need to spend more time on that, but that is the take home for that equation of like this part of the integration. Cool. Yep. And sorry about breaking that integration down more. There was no reason to, because that was supposed to be the aha moment right there. Okay, hell yeah. So now we know where the neutral axis is. It's just at the center. And you would want to do a separate calculation to figure that out, but you could do that separate calculation. Alright, so now we're going to, this is brutal. I mean, all we're going to go through is this last part, but it's the moments. Due to these stresses on these areas causing forces, they're causing this moment. And we want to know, what is that equal to? So the generic form of the equation for moment is force times distance. Here's some force, there's some force. We got some distance from the neutral axis. The force is going to be sigma times area. Sigma is that axial stress as a function of y. Area is dA, and y is positive. And oh yeah, and this is where I got into trouble. I put all these asterisks because this is where you mess up. Is like, cool. So if this is the moment equation, a little fraction of moment is sigma dA. You know what I mean? Y. You know what I mean? Some distance y. And if we say that my distance y is positive on this face, so y is positive, the area is positive, it's in the positive x face, but sigma is negative. So let's go through here. So if I have a positive y, I'm going to have a positive area, but this value for the stress, if y is positive, is going to be a crunching, is going to be a compression. So that's negative. And so this value right here is going to give me a negative value. this is going to equal the moment. So now let's go up onto our chart and like, hey, this is the force this is the moment of that force that we calculated, and that's going to be a positive force. So we need this side to be positive. When y is positive, this side is negative. So all we need to do is just put a negative in front of this. And so then we have negative sigma xy dAy. I'm going to substitute this equation in for sigma x of y. So we're going to have negative curvature modulus of elasticity, that's the constant, E, dA, and then this y. So we're going to have two of those y's. This negative Ka gets factored out of the integration. We're going to integrate across the area. We're going to have y squared dA. And I got to be done with this video because my battery's running dead. I'm running out of juice. But this is where the aha moment should come. Be like, oh yeah, that's moment of inertia. You know, and I think this is probably way easier to see that this is moment of inertia. Moment of area is kind of tricky. And that other proof of just saying, ooh, moment of area, and it was 0 because we're at the neutral axis. But hell yeah, so now we just have mass is equal to the negative curvature EI. So that's what we have here. Oh, did I mess up again? Yes, I apologize. I didn't catch it. So negatives will just ruin your day on this one. So we have negative sigma x dAy, but sigma x is negative Ke. So when I throw this in, I'm going to have negative, negative. And so that's going to be a positive value. And I don't know if I... Yep, so we're going to have positive Ke. Yeah, we just destroyed this one, so maybe for another day. But moment is equal to positive Kei. Yep, and yeah, I didn't double check all my asterisks through there. Now you take this equation, and this says that the moment is equal to the curvature times the material property times the shape, and I guess that's cool. And the curvature is the reason, and it should make sense. We talked about how the curvature was changing the shape. The change in shape made things shorter, made things longer. If something gets shorter, that means that it's compressing force. The force is compressing those materials. If it's getting longer, force is lengthening. And so if we have a force there and a force there, that's generating a moment. So the moment is generated by the forces. The forces are there because of curvature causing strain. I hate that word, but the change in length of those, and if we can measure those change in lengths, we can know the force. Stress, but you know what I mean. Like I said, change in length and force are synonymous, where stress and strain, you're going to lose your mind using those terms. All right. But you get better at it, but I still to this day, I think it's best to teach using different terms or just talk through those terms and tell you what they are instead of just saying stress and strain. So curvature is m, the moment, divided by EI. That's how we just rearrange that equation. And then we go, it seems like redundant or weird, but you go back to your strain your PSI equation, your strength equation, your stress. And stress is equal to modulus of elasticity times strain. We said this is equal to negative Key. We're going to throw... All right, last push. Yeah, so we get this relationship between curvature, the moment, the shape of the material, and the material itself, the stiffness, the properties, and then we can throw that value for curvature into the stress, the axial stress equation. Stress is a function of y. And negative Key, we're going to throw k into there. And so we're going to have negative m divided by EI. This is also multiplied by the modulus of elasticity. That cancels. So we get stress is equal to the moment generated, y, and then I. And the internal moment right here, we see that it's due to the forces. When we do just a beam, and we throw a moment right here and a moment right there, you know, there is no, in this situation, there is no, and if the beam is negligible weight, there's no load, there's no resultance there and there. There's no shear forces. There's no axial forces. Those are all zero. And so any chunk, free body diagram chunk, we have a moment generated there. It has to be matched by the equal moment to, because this thing's not spinning. And so we have the moment for every point along here, x. And then so, and that moment at that face is these forces. And so, so we can know this moment due to, you know, free body diagrams of the beam. We can input that number right into there. We know the y distance. Well, and then just like, I don't know if the intro video that I did the other day, I'll do that one first and then this one. And then just this stress. Anytime you're working with the stress, which is the strength, strain, these two specifically, you know, just put a ton of subscripts in. Like you could have max stress, you could have max strain, you could have minimum stress, you could have minimum strain, you could have, and then sky's the limit. Yield, plastic limits. I mean, it's just, you're just taking a number that's between 0 and a maximum. You know what I mean? And so, so this is giving us the stress, the PSI, as a function of y. So we go down the neutral axis of this beam, and we know that the fibers on the bottom and the top are going to experience the most crunching, the most stretching, the most stress, the most loads. And so, but here's that equation that relates them. So that's the proof to get to this point. And now you'd never have to do that proof again. I need to do that proof about 10 more times on video. But here you go. And if your cross-sectional area is h, your neutral axis is right here, so this is y, this is x. And if this is y, you know what I mean? Hey, your top is just going to be h divided by 2. And then so you could say, hey, your max stress is going to be, well, let's talk about this, because let's say you just put 58,000 psi. This is the max stress for steel. Cool. And then let's say the moment at that point along the beam x, we have h over 2. And then we know something about how this beam is just bh cubed divided by 12. And then so, I mean, this is where you never have to do the proof again, and you just use this equation. And even in this form, I don't really like it because, well, no, it's decent. Yeah. So there you go. So now in our problem design, we can figure out what the max moment we want. Now, for simple beams, where you just like get a beam to drive over for your like driving over a stream, and you want to go to the steel yard and get an I-beam, and you want to know if it's good. Here's your load. It's like the load of a car, maybe 2. And what's the max moment? Well, you know, I mean, you're going to have a P divided by 2, a P divided by 2. And then your shear diagram is going to be up P divided by 2 over down P over up, and then your moment diagram is going to be like that. And your moment's going to be PL divided by 2. So sweet. You know what I mean? So if that, and then let's say I know that load. So now I want to know, you know, maybe in this, I know steel is 58,000 pounds. I know my moment is the weight of a car. So the weight of the car, the length of my span divided by 2. And then the only things I don't know are half the height of the beam divided by BH cubed divided by 12. I mean, or just if I'm using an I-beam, H. You know what I mean? So I don't know these two numbers. And so that's how we size those. You know what I mean? We know the moment of inertia of a beam. And then this I divided by Y, if you flip it, is actually S. And even though you don't need it, but if you go to I-beam charts, hey, this is just a number. And so right here, I would just rearrange this equation. I would take 58,000 times 2 divided by the weight that I want the bridge. Let's say, I don't know, it'd be sweet to have a 10,000 pound bridge just to say I had it. And then the length is going to be 40 feet or 40 times 12 because we need to work in PSI inches. This is in PSI. So there you go. So even just, so that's the I'm glad I'm ending on this because it's just like, why do you do all that derivation? Is to know where the hell it came from. And I definitely graduated with not wanting to know any of, like, I don't know, but I actually excelled in high school when some of the teachers slow rolled me through the derivations. And that's what I'm recalling right now, like, you know, doing these is just like, that really helped. And so at some point in life, trying to do the slowest, longest, hardest way is going to be the best. Because then you go into all the nooks and crannies and you're like, hey, there's nothing more. You know, especially with like differential calculus, integral calculus. You're just like, I don't know something, but you think there's a vastness that you don't know. When really it's just a room, go explore the edges and nooks of the room, and then that's all there is. And then I think once you know that's all there is, your brain can be at peace and kind of fully grasp a concept just a lot better. All right, hell yeah. So, so for this, we got 58,000 times 2 divided by 10,000 divided by 40 divided by 12. All right, so, I feel like that didn't come out good. Is that right? I feel like we royally messed something up. I think the moment's PL divided by 2. But yeah, so I would have so I would have 10,000 times 40 times 12. That's going to be a really big number in pound inches. Moment's going to be in pound inches. Yeah, it's going to be reverse that. So I need to get the S value up here. I'm going to take this divided by 58,000. Sorry about that. And I get an S value of 82.7. So hopefully I did it right. All right, hell yeah. And then so I just go to the I-beam page, and it's cool. We had a steel yard in my town, and you can just go buy I-beams. You know what I mean? They'll load them on your truck. I don't know how you're going to get them off. They weigh hella. 30 pounds per foot, 60 pounds per foot. So this is the weight per foot. The 10 is the height of the beam, just nominal. And then it's a W. W doesn't mean weight. It just means that it's a W. It's a wide flange beam. I'd call them I-beams, but people call them wide flange beams. I-beams are narrow, and the true I and their S, they're definitely more curvy on the inside. Anyway. More for vertical loads. These can be loads in 4 directions. Anyway, so S of 82. So I'm just going to go down here, and let's see where we get the first one to say 82. This is 100. So maybe like right there. So and I think this is. Oh, but check this out. Do you think I'm just going to drive across one of them? No, I'm going to have 2. And we already said 10,000, which is plenty for a 5,000 pound car, whatever. And then so my S value only has to be 41. Never thought about that. If I put 4, 2 under each wheel, I could get down to 20. You know what I mean? So now, like, hey, the lowest one is something that weighs 21 pounds per foot. So that's 21 times 40. That's 840 pounds. But still, you could muscle that around. You know what I mean? So without too much equipment, it's pretty friggin' heavy. But still, you can get some winches. You figure out a way to get that. But yeah, you could have 4 I-beams and do it yourself. Or you would go get, like what's one's, yeah, the first one with 40 weighs 45 pounds per foot. And steel costs about $2 a pound. So 45 pounds times 40 times 2 of them times $2. You know what I mean? So hell yeah, building a bridge is hella expensive. Sometimes it's $1 a pound. I don't know what the price of steel is doing lately. But yeah, 5,000, you know what I mean? So nothing's cheap. $5,000 to $10,000 to make a hella long 40 foot bridge. But anyway, just the fact that you can just get that S value and just be on your way. So hell yeah. So that's the whole idea with deriving the bending moment equation, is to get down to an equation that you use. And there's a lot of equations in this book. This is probably the main one. Just because every beam you have to, this is, steel is hella strong axially, but the second you make a span, man, it doesn't take much. You know, you 10x to 100x lower the load that you can put on it compared to just axially loading an I-beam. You know what I mean? Sky's the limit on that. So I might be off by another factor of 100. Alright, hell yeah. So that's the equation. And that's it. That's all I got. We did it. That was brutal. But I think it's good. It's good to, if you're not making videos, like, who the hell are you talking to? You know what I mean? If you're just, like, rambling it in your head, some people are just good. They're just smart, and they're just like, oh, hell yeah, all this sticks. I don't need to tell anyone because they're not going to learn it anyway. But, yeah, I don't think I've ever thought I'd ever talk my way through it. But obviously we ramble, and but it is, yeah, if people are still benefiting from it, I'm still going to do it. So, booyah.